बहुत आगे पीछे होगा तो वो मैं एडिट कर लूँगा, ठीक है। चलिए, हाय हेलो, आवाज़ आवाज़ सब आ रही है ना? ये आवाज़ का, अच्छा, उसमें रिकॉर्डिंग का पता चला, ठीक है। हाय हेलो, I hope that all of you are doing great. My name is Shivam Gandharv. I am physics faculty, and in today's session, I will be taking the Gauss theorem and application related to Gauss theorem. So let us start our lecture. So basically, uh, there are a few things that you need to know before knowing the Gauss theorem. Right? First of all, first is the flux. Right? You have to know that what is flux. So basically, we know that if there is some charge, that charge would be producing some electrical field like this, right? That electrical flux, sorry, that electrical field, if passes through a region or not region, a area, right, that give us some flux. So we can say that total number of field lines crossing a area is called flux, right? So first of all, we have to understand what is flux. Flux is number of field lines crossing a area, okay? And if you want to calculate the flux, we have to do, we have to take the cross product of electrical field and area, sorry, the dot product of electrical field and area. So to calculate the flux, we have to calculate the dot product of electrical field and area. Now, how we calculate the dot product of electrical field into area and area? Suppose we have some electrical field, right? And there is some area. So electrical field is in this direction, while some area would be in this direction. So as you know that area is a vector quantity, so it would have some direction. So direction of area is given by a perpendicular line, a line that is perpendicular to area itself, right? So that would give us area vector. So suppose this is area vector dA and this is electrical field. So there would be some angle between them, right? So there would be some angle between them. And if we take the dot product of electrical field and area, that would give us the flux, right? So basically flux is electrical field dot dA, or we can say it is electrical field into small area times the cos theta, where theta is angle between area and the field lines. All right. So this was basic idea about the electrical flux. Now let us understand the Gauss law. Gauss law or the Gauss theorem. So basically it tells us that suppose if we have a closed shape, if we have a closed three-dimensional shape, and if there is some charge inside, there's some charge inside this closed shape, so there would be some field coming out from the field lines coming out from the charge. So total number of field lines coming out from the charge, or total number of field lines that is crossing this area, should be directly proportional to charge, right? So we can say that flux coming out from this closed shape in which some charge is enclosed is directly proportional to the charge that is enclosed inside the three-dimensional shape, right? So flux coming out from this closed shape is directly proportional to charge. Now, what do you think? Does flux depends on the shape of the charge? Does flux depends on the area? Does flux depends on the position of charge? Think about it. Or it just depends on the charge that is enclosed inside this closed shape. Okay, I will try to visualize it, right? So suppose I'm just using a new slide for that. Suppose we have a charge over here and there are some field lines from the charge. So these are the field lines from the charge, and suppose here we have a closed shape, right? So you know what is flux? Basically flux is number of field lines crossing the area is called flux. So if we keep a charge over here, if the charge is outside, so number of field lines entering the shape are equal to number of field lines, exiting the shape or emerging out of the shape. So there is no contribution of the charge in the net flux through this closed shape. But once this charge is inside, now you can calculate how many field lines are coming out from the shape. It's 1, 2, 3, 4, 5. Yeah, 4 plus 4, 8. So if I, change the position of the charge, it would not have any effect on the flux, right? So the flux coming out from this charge does not depends on the position, neither it depends on the size of the area or size of the closed shape. So if the closed shape is even bigger, the number of field lines crossing this shape would be same. So Gauss law says that the number of flux or the number of field lines or the flux crossing a closed shape is directly proportional to charge that is inside this shape. Okay, that is what called the Gauss law, right? And the value of flux should be equal to charge by epsilon naught, right? It should be the charge by epsilon. This is what the Gauss law is, right? Now, we have a proof of Gauss law, but let us directly jump onto this application. So we will be learning about the application of Gauss law. What are the application of Gauss law? So far we know that if we have a charge enclosed in a closed shape, right, the flux coming out from the charge is directly proportional to charge inside the shape. Or we can say the closed integral of E dot dA should be equal to charge inside the shape by epsilon naught, right? So this is the flux that is leaving this shape. Okay, now we can use this law, we can use this theorem to prove or to find the electrical field by various shapes. For example, using this, we can find the electrical field by a uniformly charged solid sphere. So now I am going to find the electrical field by a uniformly charged solid sphere using the Gauss law. Fine. So first of all, we would consider a uniformly charged solid sphere, right? So here we have a uniformly charged solid sphere and charge is distributed evenly on it, and we want to find the electrical field at some distance from the center. So let's say capital R is the radius of this uniformly charged solid sphere, and we want to find the electrical field at some distance x from it. Okay. Now, to find the electrical field, we have to assume that there is some electrical field at this point. Let the electrical field be E. So E is the electrical field. And we have to consider a Gaussian surface that is symmetrical to this entire shape. Okay, so the Gaussian surface that is symmetrical to the entire shape would also be spherical. So consider a spherical Gaussian surface over here, right? So this dotted one is the spherical Gaussian surface. Now we want to find the field over here. If you see the angle between this electrical field and area vector at this point, the area vector at this point would also be in the same direction as that of electrical field. So theta would be 0 between them. If you want to find the flux through this, entire shape, we can write it as closed integral of E dot dA should be equal to charge enclosed divided by epsilon naught. Remember, this Q is not the entire charge of the sphere. Instead, this is just the charge inside this Gaussian surface, not the entire surface. Okay. So, all right. We can assume that capital Q is the charge on entire sphere. Okay, it is charged on entire sphere. So we can do closed integral of E dot dA. Now at every point, the angle between electrical field and area vector would be 0. So we can consider cos 0, and cos 0 is 1 everywhere. Okay, so we can write it as electrical field, and electrical field is constant. So remember, area and electrical field, they are in same direction, and electrical field is constant. So we just have to do E into closed integral of dA. It should be equal to charge enclosed divided by epsilon naught. Now, next is, what does it mean? Closed integral of E dot dA. Sorry, closed integral of dA. It means that if you take small area and you repeat the same thing with this entire surface, so that will give you the closed integral of dA. And in another language, I can say that this entire area of this sphere is equal to closed integral of closed integral of dA. And we know the formula for area of a sphere, that is 4 pi r square. So I can say E times 4 pi r, or radius over here is x square, should be charge enclosed by epsilon naught. Now the only challenge is to find how much charge is inside this sphere, inside the Gaussian surface, I would say. So if you want to find the Gaussian charge inside this Gaussian surface, I can do it in one way. Just take the density of this entire sphere times the density by the volume inside the Gaussian surface. Then that will give us the charge inside the Gaussian surface. All right. So let us see. We can say the density is charge over entire volume, and entire volume is given by 4 by 3 pi r cube. This would give us the entire density. And to find the volume inside the Gaussian surface, we can times this by 4 pi x, times it by the volume inside this Gaussian surface, that is 4 by 3 pi x cube. Okay, so density times volume, the volume of the Gaussian surface, or volume inside the Gaussian surface, is 4 by 3 pi x square. And if I times this density by the volume, I would be getting the charge inside the Gaussian surface, right? So the charge inside Gaussian surface can be written as Q n closed should be equal to Q by 4 by 3 pi capital R cube times 4 by 3 pi x cube. So this 4 by 3 pi and 4 by 3 pi would cancel out each other. So charge inside the Gaussian surface can be written as Q by R cube times x cube. Let this be equation 1 and let this be equation 2. Now, if we put the value of charge from equation 2 into the equation 1, then we can get what flux is. So one flux we can calculate by the Gauss law, another flux we can calculate by closed integral of E dot dA, and just put them equal, right? So that would give us electrical field times 4 pi x square. It should be equal to Q R cube times x cube divided by epsilon naught. Okay, so from here x square and cube would cancel out each other, and we can write it as, if we put 4 pi over here, r cube over here, then we would get the value of electrical field as 1 by 4 pi epsilon naught q x over r cube. So this will give us the value of electrical field as a function of x, where x is the distance from center. Okay, so if you draw the graph would be a straight line. So electrical field versus x graph would be a straight line. But remember, this formula of electrical field is just valid up to where x is equal to r cube. If we go outside, their x would be greater than r. In that case, we can consider this entire shape as a point charge to find the electrical field. And the value of electrical field is kq by x square outside it, right? So it would go straight until r is equal to x, and after that it would follow the point charge or follow the inverse square law, right? So this is the electrical field by a uniformly charged solid sphere, and we have just calculated it by using the Gauss law. All right, so we can we can find the electrical field by similar shapes using the Gauss law. Let us try. Next, I would find the electrical field inside a uniformly charged solid cylinder. And that we would be doing using the Gauss law. Okay, so first of all, let here be a uniformly charged solid sphere, and the density of it is infinite actually. So it is an infinitely charged, uniformly charged solid sphere. And let the radius of this uniformly charged solid sphere be r. And we are interested in finding the electrical field at some distance x from center. So we want to find the electrical field somewhere over here. So similarly, we have to consider a Gaussian surface over here. Now, the challenge is that Gaussian surface has to be, symmetrical to this entire cylinder, right? So let us take the Gaussian surface that itself is a cylinder, and that Gaussian surface is somewhere over here, right? This is the Gaussian surface, and we are interested in finding the electrical field. This Gaussian surface would also be like this. Okay, we are interested in finding the electrical field at this surface. Okay, so there are a few conditions which are valid over here. First is the electrical field is perpendicular to the surface. Yes, electrical field is perpendicular to the surface over here. Second is electrical field should be uniform everywhere, throughout this entire cylinder, the Gaussian cylinder. Yes, it is uniform, right? So then we can apply Gauss law. That would be beneficial for us. So if you apply the Gauss law over here, we know that flux can be calculated in two ways. One is closed integral of E dot dA, and next is by Gauss law. So by the Gauss law, electrical flux should be charged enclosed inside the Gaussian surface divided by epsilon naught. Okay. Now, how much charge would be there are a few things that we have to assume. First is the density of this cylinder. So let density of cylinder be rho. So rho is the density, charge density of this cylinder, right? So if you want to find the charge inside this entire Gaussian surface, so charge enclosed inside this Gaussian surface can be found by using volume of the Gaussian surface times the density. Okay, so if we want to find the volume of the Gaussian surface, we have to consider its length. Let the length of the Gaussian surface be L and its radius would be x. So volume should be pi r, or the radius is x over here, pi x square. That would give us the area of this cross section of this cylinder. Pi r square times length. This entire thing will give us the volume of the Gaussian surface, and then we have to times it by the density. So this would give us the charge inside the Gaussian surface. Okay, so if we put this value of flux can be calculated by electrical field into area. Now, which area this is? This is the area of Gaussian surface through which electrical field will pass. Now, the direction of electrical field will be this one, but area vector over here would be this one. So area vector at this point is perpendicular to the direction of field. So there is no flux that would come out from this part. neither there is any flux coming out from this part. So entire flux would be coming out from this curved surface area of the Gaussian surface, right? So flux would only be passing through this curve. Now, if we want to find the flux, we can take electrical field times the curved surface area. Curve means this one, this surface. So curved surface area will be 2 pi x times L. Okay, so this is flux and this is also the same flux. And if we put the value of charge from here, it should be pi x square L rho by epsilon naught. So this is also flux, this is also flux, and the flux should be same. So we can just equate them. If we equate them, then we can get electrical field into 2 pi x L should be pi x square L rho by epsilon naught. Okay. So from x and x, they would cancel out each other. Pi and pi would also cancel out each other. Okay, so we can write it as electrical field is, yeah, L and L would also cancel out each other. So it should be rho times x by 2 epsilon naught. Okay, so that would give us the electrical field by a electrical field inside a uniformly charged solid cylinder. Okay, I hope you understand this entire concept. Okay, so now we will find the electrical field inside a Gaussian. Now we will find the electrical field inside a uniformly charged solid sphere where there is a cavity. So basically, we are going to find the electrical field inside the cavity. So suppose this is a uniformly charged solid sphere and its density is given as rho. So rho is density of uniformly charged solid sphere, and we have a cavity, and this cavity, the center of the cavity is, let's say, at a distance a, while the radius of this entire shape would be r. So we want to find the electric field somewhere over here. We can do it by considering this, instead of considering it as a cavity, just consider it as another sphere whose density is same as density of this entire sphere but negative. So if rho is the density of this entire sphere, then minus rho is the density of another sphere which is placed instead of this cavity. So don't assume it as a cavity, right? So if we see the electrical field at any point, the electrical field will depends, the resultant electrical field will be resultant of the electrical field of this entire sphere and electrical field of the cavity, or not cavity, in electrical field of a negatively charged sphere. And if we just add these two electrical field, one is away from the center, another is towards the center. Why it is towards the center? Because we are considering it as negative, right? So if we take the vector sum of these two fields, that will give us the resultant electrical field. So it is E1 and it is E2. So we can find the electrical field as by E1 as rho times, let the distance from here be R1 and let this distance be R2. So this distance is R2. So electrical field by this completely charged sphere, or the bigger charged sphere, should be rho times R1 divided by 3 epsilon naught, and its direction would be along the direction of this line joining 2 points, the point where we want to find the electrical field and the center. And E2 is electrical field by this negatively charged solid sphere whose density is minus rho. R1 is the distance from this center times 3 epsilon naught. So if we add these two electrical field, we would be getting the resultant electrical field. So the resultant electrical field is E1 plus E2. So E1 will be rho R1 by 3 epsilon naught, and E2 will be minus of rho R2 by 3 epsilon naught. So we can take rho and 3 epsilon naught as common. R1 minus R2. Okay. So this is R1 and this is, R2. So if we take away R2 from R1, their vector sum would give us the line joining their centers, right? That would give us the line joining their center if we are just adding them. And why I'm taking it as negative? Because it is towards the center, right? So that will give us rho by 3 epsilon naught. This line represents the A vector. So the electrical field in this entire sphere is independent of R1 and R2. It is just depending on the vector that is equal to line joining these centers, right? So in electrical field in this entire cavity would be a constant, and that constant has a value of rho A by 3 epsilon naught, where A is in vector form. Okay. And this electrical field has a density that is independent of its position, and it would be constant, and it would along the line joining two centers. So the electrical field in its entire sphere would be some way like this. Like if this is the entire sphere, this is the cavity, so electrical field is uniform inside this cavity. Okay, so I hope you understand all these things. Goodbye, take care, we'll be meeting soon.